So in this video we'll be learning how to find the inverse of a matrix. So let's look at the simple definitions first and rules. So assume that we have a matrix A which is n by m times. There is a inverse of A such that A times A inverse A is equal to identity, and the other way around also. So what I mean by identity is, let's say we have identity 2. If you don't know what this is just simply 1 1 0 0, and identity 3 will be 1 1 1 0 0 0 0 0 0. So very simple. So that's all for this one. And we also have that the determinant of A inverse is equal to 1 over inverse determinant of A. So that's another rule, very important rule you have to remember. And the last and most important rule is that the inverse of a matrix only exists if the determinant of A is not equal to 0. So if it is equal to 0, there is no inverse, basically. And let me also, another important thing in inverse in matrices generally, the order is very important. So what I mean by that is, if we have A, B, where A is a matrix and B is a matrix, is not the same as B and A. So we have to be very careful of the order. And the same with inverse also. So if it's A inverse times B is not equal to B times A inverse, like this. So keeping that in mind, let's try to solve this example we have. So if A and B is equal to C and we want to write in terms of B, we have to multiply A inverse from the left side. So multiply A inverse from left. So this left is very important, and this will be equal to, so this will cancel out since it will be identity times B, and anything times identity is just itself. And here it will be inverse, one second, A times C. So just because we multiply from the left side, that's why the inverse of A is here. So now using that previous rule of if the inverse only exists if the determinant is not equal to 0, try to solve this example. So the first one, and if you don't know how to find a determinant, I made the video recently, so you can go and check that out. So for the first example, the determinant is equal to 0. So this means this is not invertible. For the second one, we get the determinant as let me check, negative 26. So B inverse is equal to negative 26. So it is invertible. So very straightforward. And for the last example, this is not a square matrix, so meaning that the number of columns is not equal to the number of rows. So this is also not invertible. So now let's learn how to find the inverse of a 2 by 2 matrix. So assume that we have a matrix A where A is equal to A, B, C, D. The inverse of A is equal to 1 over determinant of A times, we flip A and D and we put negative signs on B and C. So very straightforward, and let's look at one example. So we have a matrix A which is equal to 3, 4, 5, 6, and we want to find the inverse of it. So first step would be to find a determinant, which is going to be 3 times 6 minus 20. So A determinant is equal to negative 2, and now we use this rule here in the yellow. So 1 over negative 2 times, we flip A and D, so it's going to be 3, 6 and 3, and we put negative signs on 4 and negative 5. And now we just simplify, so we get negative 3 to 2.5 and negative 1.5. Very simple and straightforward. Also, this is another very simple rule. The inverse of any diagonal matrix is the 1 over the diagonal itself. So let's look at one example here. So here we have matrix A, which is equal to this, and we want to find the inverse of it. So it's a diagonal matrix, meaning it only has elements on the diagonal. So the answer will be 1 over 3, 0, 0, 0, 1 over 5, 0, 0, 0, 2, and that's it. So now let's look at how to find the inverse of a 3 by 3, which is very tricky. So here we have a 3 by 3 matrix, and we need to use Gauss-Jordan elimination to find A inverse. So to find the inverse of a 3 by 3, you need to know how to find RREF. So I did that in my last video, and I'll be doing it right now also. So let's get to it then. So the first step is to write the matrix and write the identity matrix of itself also. So this is the way. And now what we have to do is we have to do the RREF for this section, and whatever answer we get over here will be the inverse answer. So let's start by doing that. So first step would be to use the first row to get rid of the second row, 2, and this 3 here. So we need to do minus 2r1 plus r2, and then also minus 3r1 plus r3 to get rid of this 3 here. And if you don't know how to find the RREF, you can check my other video. I explained it very thoroughly there. And we get the answer of this first row stays the same, second row becomes 0, 2, 7, third row is 0, 3, negative 11. So you have to be very careful here, because this is very prone to silly mistakes. And I have a negative 7 here, yeah, sorry. So here is going to be 1, 0, 0, and then negative 2, 1, 0, and then negative 3, 0, 1. Close this. Now we do now we add negative 1, the negative of row 3 to row 2 to get this as negative here. So we can flip that and then use that 1 to cancel this out. So we get now, I'll write it down here. First row is the same, second row becomes 0, negative 1, 4, and third row is the same also. Also, there is a way on the calculator to find the inverse of anything, so you can always use that to recheck your answer. And 1, 0, and then 1, 1, negative 1, and then negative 3, 0, 1. So now we find the negative of r2 to make this 1 and use that to cancel this out, and the 1 above it because we're finding RREF, not REF, because RREF is unique and the inverse is also unique. So now we get 1, 1, 2, then 0, 1, negative 4, and then 0, 3, negative 11. Here we get 1, 0, 0, negative 1, negative 1, 1, negative 3. Okay. Now we use this row to get rid of this one here above it and below it. So we do negative 2 r2, r2, negative r2 plus r1, and also negative 3 r2 plus r3. Let me just make more space here. So after this we get 1, 6, 0, 1, negative 4, 0, 0, 1. So now we just use this last 1, 0, 0, 1 to cancel the ones above it, and we'll get the final answer. So let me just write this here. So this method is quite long, and it's very common to make a silly mistake here. So be very careful when you're doing this. And again, you can recheck your answer using the calculator. Oh, there's a negative 1 here. And now we use this to get rid of this. So negative r3 plus r1 negative 4 r3 plus r2, and the final answer here you'll get this So this is the identity of 3, and this is the inverse section, which is 2, negative 17, 11, negative 1, 11, negative 7, and then 0, 3, negative 2. So this is the inverse on this side. So the final answer here is this. So here are some conditions that if one of these conditions is true, then all of the other conditions are true also. So let's say if we find that the determinant is not equal to 0, then straight away we can say that the RREF of A is equal to identity. So let's look at one example where I can explain this more easier. So here we have a question where it says we have to find the RREF of A, where A is equal to this matrix here. So one quick step we could do is we can find the determinant, and if it is not equal to 0, then we can directly just say the RREF is equal to the identity of 3. So let's find the determinant and choose this column here where it is 0, 0, 2, and we get A determinant equals 2 of 2, 3, 0, 3, which is equal to 12, which is not equal to 0. So the RREF is equal to of A is equal to 1, 0, 0, 0, 1, 0. So that saves you a lot of time and not doing the RREF manually. So here are two conditions, two rules you have to remember, because these will be used in solving for proving questions. So the first one says that the inverse of A transpose is the same as writing the inverse of A transpose to the power of transpose. So that's one rule you have to remember, so that you can swap these two signs. So that's a simple way to remember it. And the other crucial one is that the determinant of A inverse is equal to 1 over the determinant of A. So now let's look at some proving questions. So here we have a question, says that if A is symmetric, then A inverse is also symmetric. So we have the given as, so the given is A is symmetric, meaning that given A transpose is equal to A. This is the given. So if the question is saying that the A is symmetric, the transpose of A is equal to A. So and we want to prove would we want to prove that A inverse is also symmetric. So want to prove A inverse is equal to A, yeah, this is what we want to prove. So looking at the rules from before, let me just remove this bracket. So look at the first rule and try to apply it over here. So we know that A is symmetric. So let's take the right side over here, which is this part. So right side, oops, we have is A this transpose. So now as the rule says, we can flip the signs. So we get A transpose to inverse. And as we know that A transpose is equal to A, so we can replace A transpose with A here, and we get the same as this. So this left hand side is equal to the right hand side here, and we prove that. So here the second question is, we have the given as if A inverse is equal to A transpose, then we need to prove that the determinant of A is equal to plus minus 1. So let's write the given first of all. So A inverse is equal to A transpose. So I'll just start with the given. And whenever you want to prove something with determinant, you always take the determinant. So no matter what, if the question has in the proving part that there's some determinant, just take the indeterminate of both sides. So here, if we take determinant of A inverse, we have to use this rule here. So we use the second rule here. So we get this, and as you know from the rule, second rule here, determinant of A inverse is equal to 1 over A inverse, A determinant, sorry. And we get 1 over determinant of A is equal to A. Oh yeah, one more thing I forgot to mention is that the determinant of A is also the same as A transpose. So this is just a rule you have to remember because it's logical also. The determinant, not if you don't have the determinant. So that's it. Let me just erase that. Or you know what, I'll just leave it there. So here we can simplify, and we can take A here to the other side. So we get 1 is equal to transpose squared, and then simplify it again. A determinant is equal to plus minus. Don't forget plus minus, and we prove the question itself. So